Hey everybody. Today we're talking about the hypergeometric distribution, which models sampling without replacement, much in the same way as the binomial distribution models sampling with replacement. Let's start with an example and then we'll get into some of the more general ideas here. A bowl of Halloween candy includes 18 Snickers bars and 7 Butterfingers. A kid's going to take 5 candy bars at random. We'd like to know the probability that exactly 3 are Butterfingers. So obviously here we're doing sampling without replacement, and there are exactly 2 possible outcomes from each sample. You can either get a success, which is to say a Butterfinger, or a failure, which for this kid is a Snickers. So we need to count the number of ways that the event can happen, where you get the right number of Butterfingers, and then divide that by the total number of possible outcomes, the total number of ways to draw 5 candy bars from a collection of 25. So let's start with the number of ways that this event can occur. If we need to get 2 Snickers and 3 Butterfingers when there are 18 Snickers total and 7 Butterfingers total, the number of ways we can do that is 18 choose 2, that's the number of ways to get the Snickers bars, times 7 choose 3, that's the number of ways to get the Butterfingers. That math all works out to be 5,355. Meanwhile, the total number of possible selections is 25 choose 5, because there's 25 total candy bars in here, and the kid is drawing 5 of them when order does not matter. That works out to be 53,130. So overall, the probability that they get 3 Butterfingers and 2 Snickers is 5,355 divided by 53,130. It's just a little over 10%. More generally, suppose we're going to draw n times without replacement from a finite collection that has n1 successes and n2 failures. Let's let x be the number of successes that we get. The probability mass function of x is n1 choose x, that's the number of ways to get x successes, times n2 choose n minus x, that's the number of ways that the rest of the outcomes, the rest of the draws, can be failures. All divided by n1 plus n2 over n, that denominator being the total number of ways that you can draw a sample of size n from this population. A random variable with this probability mass function is said to have a hypergeometric distribution with parameters big N1, big N2, and little n, and that's sometimes abbreviated as hyper N1, N2, little n. To take this Halloween candy example just a little bit further, let x be the number of Snickers bars obtained in 5 draws. We have parameters N1 is 18, total number of Snicker bars available, N2 is 7, total number of non-Snicker bars available, Butterfingers, and little n equals 5, the total number of trials we're doing, the total number of draws we're taking from this bag. The probability mass function is 18 choose x times 7 choose 5 minus x divided by 25 choose 5. And the support is 0, 1, 2, 3, 4, and 5. You can either get 0, 1, 2, 3, or 4, 4, or 5 Snickers bars when you draw these 5 out. The support of a random variable with hypergeometric distribution is usually the integers from 0 to n. Remember, n is the total number, the total sample size, including 0 and including n. But that can be reduced a little bit when either n1 or n2 is smaller than that sample size. I've written out the technical version of the support here. It's all the integers inclusive from the maximum of 0, little n minus n2, all the way up to the minimum of little n, big N1. For instance, if you have 20 candy bars selected from that bowl that had 18 Snickers and 7 Butterfingers, the number of Snickers bars that you get, the value of x here, can't be less than 13 or more than 18. There just aren't enough candy bars to get numbers outside that range. The mean and variance of the hypergeometric distribution with these parameters are easiest to write and remember using the shorthand capital N is N1 plus N2, so that's your total population size, and P is N1 over N, the initial proportion of successes in that population. Then the expected value of a random variable with this distribution is N times P, and the variance is N times P times 1 minus P times big N minus little n over big N minus 1. And those formulas are easier to remember because they're so reminiscent of the formulas for the binomial distribution. where the expected value is n times p and the variance is n times p times 1 minus p. In a nutshell here, when you're sampling without replacement, you have the same expected value as if you were sampling with replacement, but the variance is lower. One more example. A statistics class consists of 16 women and 12 men. Write the probability mass function for x, the number of women chosen on a random team of 6 people. And you then use that probability mass function to compute the probability that x equals 4. Find the mean, variance, and standard deviation of this random variable. So as usual, I recommend pausing the video here, trying this on your own before watching my solution. So the parameters here for this hypergeometric distribution are n1 is 16 successes, 16 women available here. n2 is 12, that's the number of failures, the number of men in this case. And little n is 6, the total number of people that we're going to be selecting for our team. So plugging into the probability mass function, we get 16 choose x times 12 choose 6 minus x all over 28 choose 6. And in this case, the number of women we get for that team can be 0, 1, 2, 3, 4, 5, or 6. In particular, we can plug in 4. We get 0.319, so there's about a 32% chance that this team includes exactly 4 women on that 6-member team. Using these numbers, using these parameter values in our formulas for mean, variance, and standard deviation, plugging in, simplifying, we get that the expected value is 3.43 approximately. The variance is about 1.20, and the standard deviation is about 1.09. On average, on a team with 6 people, you'll get 3.43 women, and on average, the number of women on a randomly chosen team will differ from that expected value by 1.09.